Hi guys, today what we'll be talking about is the essentials of organic chemistry. Me and my partner Katie will be discussing the following. Here's an overview we'll be talking about for this discussion. First we'll be talking about what organic chemistry is, what is an alkane, how do we notate alkanes, how do we structure alkanes, what are alkenes and alkynes, how do we develop structures for alkenes and alkynes, how can we differentiate the three forms, what are functional groups, and to wrap up, we'll do a summary and a Q&A. Now, let's talk about what organic chemistry is. Organic chemistry is a branch of or unit of chemistry starting carbon and hydrogen-based compounds, which can be further synthesized, decomposed, and structured. Although there are other compounds that contain the other elements, they all have at least one carbon and hydrogen atom, thus being organic. Now let's talk about what an alkane is. An alkane, or paraffin, is a saturated hydrocarbon consisting of only carbon and hydrogen. All alkanes have a suffix of ane, ane. Another characteristic of alkane is their single bonds, as shown in the example to the right. Another characteristic is that alkanes are odorless, colorless, and barely reactive. Now, how do we notate alkanes? Alkanes have a similar rule, which is the suffix of ane, as well as a prefix, which is shown to the right. Based on how long the longest chain of carbon is within the structure, will it determine the prefix for its notation. So, in the example shown in the bottom right, we have 9 carbons in the main chain, which can be further described as nonane. And we also have side branches within this entire compound, and we can determine that we can determine a name for it, and we can do this using the suffix of yl instead of ane. So what we're seeing here is 3 compounds that are similar: CH3, CH3, and CH3. Now because there's one carbon for each, it's methyl. And because of 3 of the same kind, we say as trimethyl. So if we put that all together, we get trimethylnonane. Now these are the rules we can use to determine these structures and notations. First, count the number of carbons within the longest possible path or chain. Number all carbons for all side branches with its lowest number. So in this case, it'd be tri. Name that side branch once a number has been identified, methyl. If there is more than one side branch, name them alphabetically. So if there was a case where it'd be ethyl and methyl, you'd say ethyl first and then methyl second. Furthermore, use hyphens to separate numbers from words. And finally, use commas to indicate separation between side branches. An example is shown. Now the 2, 4, and 7 represent the placement of the side branches within the main branch. So if you look in the example shown here, at number 2, the second carbon, there is a branch there, thus y is 2. The 4th position of the carbons, there is a side branch as well as the 7th. Now, how do we structure alkanes? Knowing the alkanes notation, we now need to know how to structure it. Now, essentially what we have to do is establish the amount of carbons, as shown in the picture above, then fill in lines representing bonds relative to the carbon atoms and their valence electrons. So, because carbon has 4 valence electrons, we have to replace those electrons with bonds, and then connect them furthermore to hydrogen, which brings me to my other point. Fill in the other side of the single bonds with hydrogen per line, or synthesize it into an equation like so. And finally, if there is a side branch, repeat the process again at the main carbon location. What this means is that if there was a carbon as well as a carbon connected carbon connected to it, thus a side branch, we'd have to do that entire process again in order to fully construct the full compound. Now CH3, CH2, and CH3 represent a simplified version of what would be in store for the picture above. Now let's talk about what alkenes and alkynes are. An alkene olefin is considered to be a variant of an alkane with the alteration of double bonds instead of single bonds. Another characteristic of this type of compound, is the suffix of ene, ene. An example would be butene instead of butane. Now let's look at alkynes. Alkyne acetylenes are considered to be a variant of alkanes with the alteration of triple bonds instead of single bonds. A compound that abides by this ruling is the suffix of yne. Butine would be an example of it instead of butane or butene. A note for this would be that the structures of alkenes and alkynes also have an effect on notation which can be further analyzed. Now, what I've done here is that now that we know that where to place hyphens and side branches, what if I told you there was another hyphen? An example of this new hyphen would be to identify the placement of double or triple bonds. An example is shown to the top right and the bottom right to show an example of. In the top right we have a double bond, and the number in between both hyphens is used to indicate the double bond location. An explanation is shown to describe the complete mechanics of how to construct the structure, essentially. Another point to keep in mind is the phrase di in between double bond prefix and suffix. So if you had heptene, it would be instead called hepdie. Another thing to look at is the bottom right, which is the triple bond, and alkyne. In between the hyphens is the number 3. Again, this is used to indicate the triple bond location. The same concept of hyphens apply to the placement of where double and triple bond is located, in reference to the separation between words and numbers. Now, my partner Katie will further finish this.
So how do we tell the difference between these three forms? There are ways to determine whether a structure is either an alkane, alkene, or alkyne. Alkanes end with ane, alkenes with ene, and alkynes with yne. Alkynes have triple and single bonds, alkenes have double or single bonds, and alkanes only have single bonds. Alkenes have di between their prefix and suffix. Alkanes have one hyphen, while alkenes and alkynes have two hyphens. Functional groups. Function groups are specific groups of atoms or bonds within molecules that are responsible for the molecule's characteristic chemical reaction. Molecules in the same function group will undergo the same or similar reactions to each other. Alkanes, alkenes, and alkynes are all examples of different functional groups. While there are many different functional groups, there are 8 groups you will need to know in addition to the 3 previously mentioned. Like alkane, alkyne, and alkene, they all consist of carbon and hydrogen atoms. R represents the parent molecule, O represents oxygen, N represents any hydrocarbon group, basically any group shown on the image. The first 3 functional groups you will need to know are alcohol, ether, and amine. The next 5 you'll need to know are aldehyde, ester, ketone, amide, and carboxylic acid. In summary, functional groups are specific groups of atoms or bonds within molecules that are responsible for the molecule's characteristic chemical reaction. Molecules in the same function group will undergo the same or similar reactions to each other. Alkanes, alkenes, alkynes are all different functional groups. While there are many different functional groups, there are 8 groups you'll need to know in addition to the 3 previously mentioned. Like alkane, alkyne, and alkene, they all consist of carbon and hydrogen atoms. R represents the parent molecule, O represents oxygen, N represents any hydrocarbon group. Composed of practically all elements with at least 1 carbon and 1 hydrogen atom. For each of the following diagrams, identify the group.